Alright, we've got a handful of videos now where we just go over a lot of just different properties of exponents within the examples. So this first one, square root of 7 over the square root of 3. Now in the intro video we saw how you could take the square root of the whole thing. Well, in my mind I'm just thinking ahead and saying 7 and 3 don't reduce, so that wouldn't necessarily help us out. So we're going to do this thing called rationalizing the denominator. Rationalize the denominator. In math, we do not want to leave a square root in the bottom of a fraction. It's not simplified, there's more we have to do. So, how do we get rid of a square root in a denominator? We do this thing called rationalizing the denominator. What you do is you multiply whatever the radical is in the denominator by, by itself. Now, in a fraction, anytime you multiply the bottom by something, you also have to multiply the top. So the reason why we're doing this, what that does in the denominator is the square root of 3 times the square root of 3. We go ahead and multiply the 3's and we get the square root of 9, and it just stays underneath that square root. And then, do we know what the square root of 9 is? Yes, that's a 3. So in our final answer, we can see that we will no longer have that radical, that square root, in the denominator. You may notice as you work on rationalizing the denominator that whatever number is underneath the radical does end up in your final answer right there. So, you can, I know the square root of 10 times the square root of 10 equals 10, because the long way to think about it is the square root of 100, if you multiply the tens, which is 10. So you definitely can shortcut through that a little bit. Alright, then we multiply the square root of 7 times the square root of 3 is the square root of 21. And then I'm going to go ahead and carry that over here, square root of 21. Anytime you have a radical in your answer, you want to think, can you reduce it? Go through those numbers, 4, 9, 16, 25. Do any of our squared numbers fit into 21? And none of them do, so we can't do anything else with that. It might be tempting to say 21 divided by 3 is 7, but we can't actually divide the 21 and 3 because this is a square root of 21, and this is just a 3. So kind of think of them as being not like terms. You can't reduce them with each other. So that's going to be our final answer on that one. Alright, this next example looks a little bit weird. I'm going to go ahead, let's go ahead and see the square root of 8 as a fraction. So we're going to go ahead and multiply the top numbers and multiply the bottom numbers. Because it's all square roots, we're going to say we can multiply the 8 and the 2 and get the square root of 16. 1 times the square root of 3 is just the square root of 3. Well, the square root of 16 we know is 4. The square root of 3 is just the square root of 3. But now we're looking at having that radical in the denominator. We're going to have to rationalize this. So if you remember, you multiply the top and the bottom by the square root of 3. Square root of 3 times square root of 3 is 3. That's our shortcut. And then 4 times the square root of 3. Now we can't multiply the 4 and 3 together and say 12, because this is a 4, but that's a square root of 3. So again, they're not like terms. So that stays as 4 square roots of 3. Can we reduce the square root of 3 with just this 3? Nope, because they both have to have square roots in order for us to reduce. The other thing you want to look at is here's a 4 and here's a 3. These are, sometimes I call these the outside numbers. If 4 over 3 reduces, we would go ahead and reduce that, but since 4 over 3 does not reduce, we have found our final answer. Alright, so here we're asked to simplify the cube root of 24. Now what makes this one different is it's a cube root, not a square root. So as soon as this number changes, we have to think about a different set of numbers. We want to think about those cubed numbers that we wrote in our packet at the very beginning. So our cube numbers, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and we can continue the list. We are going to try to break this down with 2 cube root numbers. So which of these fit into 24? Well, 64 and 27 are too big, but 8 fits in 3 times. 8 times 3 is 24, and the reason why we want that 8 because the cube root of 8 is 2, and then this cube root of 3 just stays as a cube root of 3. So it reduces just like the square root numbers. The only difference is the number we put here in that first spot is coming from whatever root you might have. If it's a square root, you look at your squared numbers. If it's a cube root, you look at your cube numbers. Alright, so the cube root of 375. So again, we want to think about our cube numbers. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. And again, you can kind of go along and see if any of these fit in. Well, that 125 works. So the cube root of 125, oh, this breaks down into, there we go. So 125 times 3 gives us that 375. And then we know the cube root of 125 is 5, and then the cube root of 3 can't be reduced, so that stays as the cube root of 3.